because we've resolved it. So it's now it's a normal process. You can apply their result. Maybe, but you're absolutely right. Like, yeah, you can construct the family of subjective structures by embedding, but what's the connection of that to almost different bases? So you kind of need a result like that to say that you can
Okay, now it's working. Good.
Tamam hocam, görüyor musunuz, duyuyor musunuz?
Evet, gayet iyi.
Ha?
Gayet iyi, benim sesim geliyor.
Gayet iyi. Tamam, bir şey paylaşım, ekran paylaşımı da yapın. Sıkıntı var mı?
Tamam. Okay, I'll share my screen. So let's see. Is this okay? Or
Tam ekran.
Bunu tam ekran yapalım.
tam ekran yapalım.
Yok, biz yapacağız.
Ha, okay.
Evet, burası güzel.
Okay. No? Hocam tam ekran yapma şeyiniz var mı sizin ya?
Olabilir. Şurada var galiba, bir saniye. Daha mı iyi?
Ben daha iyi. Yazarken de biraz büyük ve açık yazarsanız daha iyi olur.
Yeni bir şey yazmayacağım. Yani bu hepsi bu fontta.
Okay, so if you can read something, just ask, okay?
Sure. One problem is if this is full screen, I may not see the Zoom part, so you might have to warn me.
Just shout.
Okay.
Just shout and you can get. Okay, so it's a pleasure to have Özgür Kişisel. He's going to tell us about Log Cy Varieties. Okay.
Thank you very much for the introduction. So this talk is intended to be an elementary talk, and it is based on the two papers. One is Mirror Symmetry and Cluster Algebras by Hacking and Kill. I think this is the ICM paper. And the other is Mirror Symmetry for Log Cy surfaces, one by Gross Hacking and Kill, and the sections written in parentheses. So I'll try to provide some extra background about algebraic geometry, which I hope might be useful. So suppose that X is a smooth quasi-projective variety over complex numbers of dimension n. So let omega be a non-zero meromorphic n form of X, then you could look at div omega, and the linear equivalence class of that is called the canonical class of X, and denoted by k sub X. Now, this might change depending on which meromorphic n form you choose. However, any two meromorphic n forms would differ by a meromorphic function, so the linear equivalence class is well defined. So up to linear equivalence, we have a unique thing. Now, let me say a few words about adjunction formula. I'll just restrict to the hypersurface case. So again, say X is a smooth quasi-projective variety over C as above, and pick a smooth codimension 1 subvariety. Now you can calculate the canonical class of Y from canonical class of X as written here. So it's Kx plus Y restricted to Y, but now in the parentheses, Vy as a divisor on X, since this codimension 1, that makes sense. And this is definitely not the most general form you can write this. There are suitable modifications if Y or even X is not smooth. One important example which will be used in this talk is when X is a smooth surface, so it's complex dimension 2, and Y is a reduced curve on X. So reduced means there are no, as a divisor, it has no multiple irreducible components. That's not exactly the definition, but in particular, it implies that. So but I don't want to assume that the curve is smooth or irreducible, so it could have singularities. In that case, a consequence of adjunction is that the arithmetic genus of y is given by this formula, 1 plus 1/2 y squared plus y times kx. So what is arithmetic genus? So for a curve, you have two possible notions of genus. I mean, in the smooth case, these coincide. But if you have a singular curve, there are two ways you could resolve the singularity, essentially. So one of them is to normalize the curve, and then the genus of the normalization would give you what's called the geometric genus. But there's another way to resolve the singularity by deformations. So more precisely, if you deform the curve in a flat family and look at one of the nearby fibers, which is a smooth curve, you could look at the genus of such a curve, and that would be the arithmetic genus. So the one that's given by this intersection number is the arithmetic genus. So I want to also go through some definitions regarding divisors. So a very good source is Lazar's book, Positivity in Algebraic Geometry. So for this purpose, let X be an irreducible quasi-projective variety over C and the Cartier divisor of X, and OXD, the invertible sheaf corresponding to D. So the general questions of interest in algebraic geometry about divisors would be, how rich are the sections of the sheaf OXD? I mean, so does it have enough sections to give you, for instance, an embedding of X into projective space? So such questions are very important, and one can ask the same questions not just for D, but multiples of D. In relation to this, a divisor is called very ample if there exists an embedding of your variety into some projective space such that OXD is pullback of O1 with this embedding map. The informal way of saying this would be, I guess, sections of OXD are rich enough to give you an embedding of X into projective space. Now, very ample is a very nice notion geometrically, but slightly easier to work with is the notion of ample. D is called ample if some positive integer multiple of D is very ample. So the difference between the two is, I guess, analogous to, for example, looking at a submonoid of positive integers, for example, generated by numbers 3 and 5, which would be a nice submonoid, but it's a little bit harder to understand compared to all positive integers, whereas, you know, ample would be like looking at all positive integers. So it's the difference between a non-saturated monoid and a saturated monoid, essentially. Okay. Now, something about Riemann-Roch. So Riemann-Roch is, in general, some important relation between Euler characteristic of a coherent sheaf and topological information about variety. So the asymptotic version is what I just want to mention here. So say X is irreducible and projective of dimension n, then you could look at the Euler characteristic of the sheaf, or X m times D. The asymptotic form tells you that the leading term, this is a polynomial, first of all, in M, and the leading term is D to the n, so D times itself n times, so it produces you a number over n factorial times m to the n, plus this big O notation. This is, the rest of the terms are less than or equal to some constant times m to the n minus 1. So the main term, the m to the n term, is governed by e to the n over n factorial. Now this is very important, but what you're usually interested in is the sections themselves. So it's H0. So you would want to know what happens to higher cohomology. So Grothendieck vanishing tells you that if X is above, so irreducible projective, and if it's a coherent sheaf on X, then if D is ample, then after twisting by a suitable large multiple of D if necessary, then the higher cohomology vanishes. Therefore,
make a connection so that the students who don't know sheaf cohomology can understand what happens if the higher sheaf cohomology vanishes to Euler characteristics. Which terms go away so that they
right, okay, thank you. So right, I was going to combine these two, so I guess that's that would answer that. So if higher cohomology vanishes, that's for I greater than 0, so H1, H2, and all the higher terms would vanish. So then Euler characteristic would be equal to H0, and then you would be able to count sections. So then these two results would say that if D is ample, then, well, in particular, you could take F equals the structure sheet O, and H0 of X, O, X, and D grows like D to the N over N factorial times N to the N plus lower order terms. Now, the notion of ample, as I mentioned, is nice, but sometimes you want to relax it a little bit, and there's the notion of Neff divisor. So a Cartier divisor on X is called Neff. If D to the power dimension of V times V, which is, you know, the right power of D that would produce you numbers, is greater than or equal to 0 for all irreducible subvarieties V of X. Now, this is related to what is known as Nakai-Moshe zone criterion. Well, if D is ample, then such numbers would always be greater than 0. That direction is sort of easy to see, but the converse is also true. So if this holds for all subvarieties, then this is a criterion of being ample. Now, so this suggests that Neff divisors, so ample divisors, if you also allow multiplications with real numbers, form a cone inside the divisor class group, or if you mod out by numerical equals, narrow severity. So this suggests that these Neff divisors should lie in the closure of that cone. So Neff divisors, the set of Neff divisors would form the closure of the ample cone. And but this is not a proof, but Kleiman's theorem closes up this gap. So the cone of Neff divisors is actually the closure of the ample cone. And one also might ask about like the asymptotic form of Riemann-Roch, can you generalize it from ample divisors to Neff divisors? And the theorem of Kolar tells you that you can do it. So if D is Neff and I is greater than zero, then the higher cohomology groups cannot grow at the largest order. Okay, so let's come to the main topic. So Calabi-Yau varieties. So let X be smooth projective for the moment, so of dimension n. So X is called a Calabi-Yau variety if the canonical class is trivial. So this would translate to saying that there exists a nowhere vanishing holomorphic n form on X. One could also define Calabi-Yau varieties through differential geometry, either by suggesting that they carry a certain type of metric, or saying that their holonomic group reduces to some smaller subgroup. But the equivalence is not at all trivial. I guess the difficult part of the equivalence of the two definitions is Calabi's conjecture, which was proved by Yau. So some examples. In dimension 1, you could look at genus 1 curves, which are C modulo lambda for some lattice lambda. So they obviously carry a holomorphic nowhere vanishing form. In dimension 2, you have K3 surfaces, which are well, one definition of K3 surfaces would be having trivial canonical class and being simply connected. If you also want non-simply connected examples, you could look at abelian surfaces again, similar to dimension 1 case. So this time you have to take C square modulo some full lattice lambda. Again, these would carry holomorphic 2 forms. I'm not suggesting that this is the whole list. So in dimension 3, one classical way to produce an example is to take a quintic threefold in K4. Now, we can see that this must be a Calabi-Yau by adjunction formula because Kx would be canonical class of P4 plus X restricted to X, but Kp4 is minus 5H and X is quintic, so as a divisor, it is linearly equivalent to 5H in P4, so the sum is 0. And more generally, it's not difficult to produce such examples, again, by repeated use of the adjunction formula. First of all, you could do the same thing with degree n+2 hypersurfaces and Pn+1. It's more or less the same computation. Or you could generalize. You could do this in weighted projective spaces. You could take complete intersections. You could do this in toric varieties where you can calculate things. But of course, these would produce you examples, but I mean, I guess you would never expect to get a full list by complete intersections. So if you want to do topological classification of all Calabi-Yau varieties, I think it's an incredibly hard problem. It's easy in dimension 1. In dimension 2, you can do it because you have classification of surfaces. And as far as I'm aware, it's not finished, but there is hope to do it in dimension 3, at least. And there's hope to precisely describe the topological types in dimension 3, but I don't know the details. Another important class of examples are hyperkähler manifolds. These are automatically Calabi-Yau. I guess the easy way to see this would be to look at the holonomy group description. So, for instance, this tells you that Hilbert's scheme of K points on a K3 surface, which is a hyperkähler manifold, is Calabi-Yau. Well, one downside is very few families of hyperkähler manifolds are known, so this provides you a small list. Okay, so coming to the title, it was log Calabi-Yau manifolds. So the idea of log geometry, I guess, is in general to study properties of non-proper varieties like affine, but keeping track of possible compactifications. So an excellent big example would be toric geometry as a subject. So what is toric geometry? So you look at an n-dimensional complex torus, C star. So C star is C minus 0. So look at compactifications of T such that the usual multiplication action of T on itself extends to the compactification. So it turns out you can do this in many different interesting ways. For example, if n is equal to 2, let's try to look at this in some more detail. C star square has many such compactifications. So the two best known are P2 and P1 cross P1. So down here, I drew the fans of these toric varieties if you happen to know the subject, but if you have never seen toric varieties, please disregard. Besides P2 and P1 cross P1, there's also Hirzebruch surfaces, which are essentially P1 bundles over P1. So you could twist the bundle, right? So the A tells you the amount of twisting. And you could create some further examples like this by blowing up any of these, maybe successively several times, at T fixed points. And it's a small theorem that these are all the smooth toric surfaces. So these are all toric examples you can create in dimension 2. But starting from dimension 3, it gets much and much richer. Okay, so I think we can make a definition of log Calabi-Yau variety at this point. So a complex variety U is a log Calabi-Yau variety if there exists a smooth projective compactification X such that the boundary divisor D, which is X minus U, is a normal crossing divisor, and Kx plus D is equal to 0. So in a sense, the first definition in the projective case is when there is no boundary and Kx is equal to 0. So this is kind of a generalization. Well, what does this mean in terms of forms? Okay, so let's say the dimension is equal to n, and this is equivalent to saying that there is a meromorphic form on X such that restricted to this big open chunk U, it is holomorphic, and it has precisely simple poles along this boundary D. So this is more like a property of the pair XD rather than U. So one usually writes the log CY pair XD, where U is understood to be X minus D. What does normal crossing mean? Well, a little bit informally, it essentially means for all points in the support of the divisor, locally it looks like a union of coordinate hyperplanes. So it's locally analytically isomorphic to a union of coordinate hyperplanes. Well, this definition doesn't tell you the number of hyperplanes. So if you have the maximal possible number, which is n, then U has maximal boundary. So more precisely, if there exists a point in the support such that its neighborhood is a union of n hyperplanes locally, then it is called maximal boundary. Okay. So as an example of log CY varieties, again, let's look at toric varieties. So take, sorry, this is, there should be some n on top here. I don't know if I can put it right away, but it should be C cross to the n. So take omega to be dz1 over z1 wedge, dz2 over z2 wedge, so far dzn over zn. So by the way, this is d of log z1 wedge, d of log z2, etc. I guess explaining the term log in the name. So take x to be any toric compactification of U, and d to be the boundary divisor. Then XD is a log CY pair. Then one might wonder, so why this works for any toric compactification? Well, informally, if you want to check that omega has a simple pole along D, this is a codimension 1 phenomenon, so it doesn't really care about which compactification is chosen. So I tried to write down an explicit example here in dimension 2. So on the upper left corner, you have P2 with 3 coordinates lines. The numbers, green numbers in parentheses, are the self-intersection numbers of those divisors. So let's take a P. By the way, this is maximal boundary because it's dimension 2, and there are points where two hyperplanes cross. So let's blow up the picture at P. Then, with some abuse of language, the strict transforms of the curves are denoted by the same letters. So, and the exceptional divisor at P will be EP. Now, that's a -1 curve. That blow-up would reduce the self-intersection numbers of F2 and F3, which pass through P, by 1, so the self-intersections drop to 0, whereas the self-intersection of F1 remains 1. Well, if you compute the canonical class, it is -F1, -F2, -F3, -EP. Still, this k plus the totality of these 4 lines is 0, so it's still log Calabi-Yau, and further blow-ups or blow-downs at the toric points will not change that. So if you blow up, for example, at this new point Q in the second picture, then you go down to this lower right corner, and then F3 becomes a -1 curve. So by Casanov's theorem, you could blow it down and get a smooth surface, and what you actually get is a P1 cross P1. So through all this process, it's always log Cy, and you just change the toric boundary divisor, and it adapts itself correctly to the canonical class. Now, just to emphasize in this example, all the toric blow-ups and blow-downs, I mean, all the blow-ups and blow-downs are toric, which means the blow-up centers are torus fixed points. Okay. Now, you could attempt to do otherwise, like not taking torus fixed points and, for example, looking at blow-ups and blow-downs there. So let's talk about non-toric blow-ups, so-called. Well, one thing we might naively want to do is to blow up at any point. For example, any point of U, the open subset, but that doesn't work because if you, at least obviously it doesn't work, because if you try to pull back the form omega, then the pullback would vanish along the exceptional divisor. So you don't get a nowhere vanishing and form on the big chunk open set. So that doesn't work. But you can do something in between. You can blow up along a subvariety of the boundary divisor, but which is not T-fixed. So an example in connection to the surface example above would be to pick P something like that. So on one of the boundary lines, but not on the corners. So that kind of blow up is called a non-toric blow up, and then it works. So this, if you do this, what you obtain is another log Cy variety. Okay, now definition of a toric model of a log Cy variety.
I'm going to say for which divisor it's log Calabi-Yau.
Oh, for which divisor? Okay. It is, let's see.
The proper transform of the form, we don't include the exceptional.
Yeah, let's see. Yeah, I think you have to do the strict transform. So, no, let's see. You have to pick, I think you have to do the total transform, but take reduced. So this is what you would have to do. So if you don't take the exceptional curve about P, it will not be compactified. So you do have to take it, but
the anti-canonical divisor is the strict transform of the group.
So sorry.
So the canonical divisor is the strict transform of the toric divisor, not the exceptional. The exceptional curve should not be part of the anti-canonical divisor after the blow-up.
Yeah, so let's see, you do the total F star and you have to add back E, so but F star contains a minus E, yes, you are right, it shouldn't contain. Yeah, it should be the strict transfer, it should be a strict transfer. That's right.
Maybe it's good to say if you could say it from the beginning so people are not, because it's important for data.
Yeah, so yeah, let's repeat that. So we want to blow up, for example, this point P, which is not torus fixed. So if we compute the canonical class of the blow up, it should be F, let's say the blow up matrix F, it would be F upper star of the canonical class here, plus the exceptional divisor. But this point is on the divisor, and it passes once through P. Therefore, in the total transform, so let's concentrate on this P2 example. So it's like minus F1, minus F2, minus F3. So the total transform would be minus F1, minus F2, minus 3, minus E, but then you add back E, so it is, again, the strict transform of the divisor. So, yes, so the new divisor upstairs should be the strict transform of the D here, not the total transform. So does it sound right? So
maybe it would be good if someone did this operation on the board and after.
Yes, discussion session after the talk, and we definitely.
Yeah, maybe you should also write it down, but yeah.
Yes, we will definitely do it after the third talk.
Okay.
But physical participants.
Okay, so what is a toric model? A toric model of a log Cy variety is a log Cy compactification xt together with a birational morphism to x bar d bar, where x bar d bar is toric and f is a composition of non-toric blowups. So something that essentially you could get pretty much as a toric variety plus some non-toric blowups. Okay, so now, okay, so you could ask questions like, are these all that you can get? So one remark is all toric varieties are rational. And so if you do some further blowups, it's again going to be rational. So all the log Cy varieties which admit a toric model have to be rational. Okay, so now a proposition in paper of Hacking and Kill, this proposition 2.10 says, if U is a log Calabi-Yau surface, so dimension 2, with maximal boundary, then U has a toric model. And as proof, they say this is an exercise in classification of algebraic surfaces. So maybe we could view this talk as trying to kind of elaborate that exercise. So here is the sketch of the proof.
Before we go into the proof, maybe does everyone kind of understand the statement?
Yeah, we could pause and.
Any questions? Okay. So log Calabi-Yau surface is an abstract definition. Okay. We are describing how all of these abstract definitions can be obtained through some procedure, which is only true in this dimension. It's not true for log Calabi-Yau varieties. Just for log Calabi-Yau surfaces, we can always present them in this form by starting with a toric variety and doing these blowups. Okay. So,
okay. Okay, so let's see. I mean, the proof somehow should show that X is rational, right? So we don't assume that at the outset. So this has to somehow come up. Now, well, step one, you could reduce to a minimal surface case, which means, okay, so what is a minimal surface? So if X contains any -1 curves, which means the curves C, which are smooth rational and square -1, then by Castelnuow's theorem, they can be blown down and you still go on with a smooth surface. And the statement is essentially unchanged, so you could reduce to the case of a minimal surface. Now, next, let's look at minimal models of surfaces. So Well, this is not the first way surfaces were classified in history, but well, you could do first a very rough classification of algebraic surfaces by looking at whether the canonical class is nef or not. So let's remember, so Kx is nef means it meets non-negatively with all irreducible subvarieties. So in this case, this is surfaces, so we should look at intersections with curves. So Kx is nef means if and only if Kx times C for a curve is greater than or equal to 0 for all curves. Now, it turns out that Kx not nef is if and only if X has so-called Kodaira dimension minus infinity, but I could explain it, I guess. So, well, not nef happens when the H0s of OM case are 0 for all positive M. I should have written positive here. And then the pluricanonical system, so-called, so the multiples of the canonical class don't give you any interesting maps. So you just get the 0 section. And this case can be classified further. So this Kodaira dimension minus infinity case just contains rational surfaces or so-called ruled surfaces, which are essentially P1 bundles over a curve C. So the complementary case Kx nef is if and only if whatever else is there. So Kodaira dimension 0, 1, or 2. Now, in our case, Kx cannot be nef. So let's try to argue that. We'll need to code some more results from classification of surfaces. Well, first of all, if Kx is nef, then Kx squared must be non-negative. So this can be seen as a direct consequence of Kleinman's theorem, for example. It has to be approximable by ample divisors, and you know that ample divisors should intersect each other non-negatively. So you get that. Well, if Kx squared is greater than 0 and Kx nef, well, this happens just in the Kodaira dimension 2 case, by the way. Then let's look at Kx times Kx plus d. Well, on one hand, Kx plus d is 0 by definition of log Calabi-Yau. On the other hand, this is Kx squared plus Kx times d, but Kx squared is positive, and Kx times d is like Kx nef divisor times curve, so this has to be non-negative, so this would be greater than 0, but this is a contradiction. So Kodaira dimension cannot be true. Well, what remains is Kx squared is equal to 0 and Kx nef. Well, this happens if and only if Kodaira dimension is 0 or 1. So there are some subtleties. So Kodaira dimension 0, there's, we already know some examples, right? So for example, K3 surfaces have trivial canonical class. But there are other interesting examples, and Kx doesn't always have to be 0 in Kodaira dimension 0, but there's a theorem that 12 Kx has to be 0. So there's some torsion business here. So if 12 Kx is 0, but you could look at 12 times Kx plus d, then 12d must be 0, but that's absurd because these some curve. So Kodaira dimension 0 case can be outruled like this. And Kodaira dimension 1 case, here you can, again, by looking at classification of surfaces, X must be an elliptic fibration, but then you have an explicit description of Kx and Kx plus d, you can again show that it cannot be 0. So all this argument tells you that X must be either rational or ruled. It must have Kodaira dimension minus infinity. Now, let's look at that case. Now, a small lemma, which is a one-line proof. D viewed as a singular curve on the surface X must have arithmetic genus equal to 1. That immediately follows from adjunction. So PAD is 1 plus 1/2 d times kx plus d, but kx plus d is 0, so this just gives you 1. So this tells you that d is rather restricted. It must be either some irreducible rational curve with a single node, just like a nodal cubic, or it could be a chain of rational smooth curves, so just like the one shown in the picture. So each intersecting the next one and coming back. Well, one also could in principle have a smooth genus 1 curve, but in that case you don't have a maximal boundary. Then you have no points which is locally analytically isomorphic to the union of two lines. So that doesn't happen. Okay, now let's show that X must be rational. The only case to eliminate is a ruled surface over a base curve C of positive genus. So why cannot that happen? Well, suppose there is something like that. So X fibers over C, the fibers are P1s, and C has positive genus. So the problem is, in this case, it is impossible to locate the boundary divisor D in this picture in accordance with the lemma above. So you want arithmetic genus 1. So then you can have at most 2 vertical fibers, because if you have 3, then if you have also a horizontal fiber, you don't have a chain. So you would have some curve intersecting three of these divisors, which doesn't work. So so you also need at least one horizontal section, but that section should be rational. So remember that in this chain of curves, all the pieces should be rational. So you would need a rational curve. But a rational curve cannot map dominantly down to a positive genus curve downstairs. So that's impossible. So the only way out is that C itself has genus 0. Then, okay, this proves that X is rational. And furthermore, ruled surfaces over P1, so P1 bundles over P1 are very well known. So I mean, if you also assume it's minimal, you essentially get just series of group surfaces, which were described above. So at least we know at this point that X can be taken as a toric variety. Now the remaining part is to take D as a toric divisor. It might not be like that at the outset, but okay, there's a small argument here which I didn't write. So if it is not so, by some further blow up and blow down, you can arrange it so, and that finishes the proof. Okay, so as Umut mentioned, this only works so well in dimension 2. The reason is, I guess, I mean, all the steps become increasingly complicated starting from dimension 3, even the minimal model program, which is itself a big thing. So in dimensions at least 3, a log Calabi-Yau pair need not have a toric model. So I'll just again quote this example in Hacking and Kill. You take a smooth quartic in P4 such that the intersection with one of the coordinate hyperplanes is like the one below. Now it's a classical theorem of Iskowski and Manin that smooth quartic threefolds are irrational. Actually, this was, I guess, historically one of the first examples where one could produce unirational varieties. So counterexamples to Lüroth's problem in dimension 3. Well, their proof uses intersection theory on such a smooth quartic and uses some ideas of funnel. So, but okay, it will give us a log Cy variety after a small change. So X is irrational. Its canonical class by adjunction formula is okay. So for T4 you have minus 5h, then for the quartic you have plus 4h. So it's minus h restricted to X, but it's like hyperplane intersecting X, so it's minus D. So if you add back this D, you get 0. The small problem is that D is not a normal crossing divisor yet. So if you look at this more carefully, it is a cuspidal singularity, but it can be taken care of by blow-ups. So again, I didn't write the details, but after some blow-ups, again, one gets a log Cy pair, but it's an irrational variety, so it cannot have a toric model. So so what works so well in dimension 2 will immediately begins to fail in dimension 3, and in the most classical examples, I guess. So this is all I wanted to say, but I was a little faster than I thought.
So maybe let's first step before, then maybe there'll be questions. Thank you very much. Can you okay. So any questions? Any online questions? Any comments?
Questions, but it is only speaking about the names. So, for example, for P2, we will have, so if we speak about the derived category, I think it will be the canonical bundle in the speaker like reality. And how this names local ideal for surface and ideal for the category connect.
Sorry, I cannot hear you very well. So could you?
So I think you're saying that the derived category is Calabi-Yau. The derived category P2 is Calabi-Yau.
So for the derived category, Calabi-Yau property is like the set of func equals to some number of shifting of complexity. I mean,
Is this true?
I think that's not true. For Calabi-Yau.
Okay.
Maybe we'll discuss in the discussion session or after the talk, because
Yeah.
so someone's asking you to post these notes somewhere. We will talk about that and make sure that happens. Okay.
Sure, I'll try. Yeah.
Vivek has a question.
What if you assume that the ambient X is rational?
What if you assume that X is rational?
If you assume X is rational, I guess for the proof you mean, or
No,
For the statement.
the statement is dimension 3.
I have no idea.
I think that
But I mean, I would suspect it's still false, but I mean, I have no idea.
Bill says that he knows.
you set it up so that the ambient variety is rational, but the boundary is irrational. And since you could get from it blow-ups and blow-downs to the center.
What if I assume the boundary also?
Yeah, well, yeah, good point. Yeah. And all the strata are rational.
Okay, so I guess the general, by assuming enough rationality, of the strata can you somehow make the theorem true? It seems like a hard enough question that no one will be able to answer. Anyway.
Still, it might be, it sounds suspicious.
Yeah.
I mean, toric varieties have, I mean, some, maybe one might have to assume something much stronger, like some extension of some integral affine structure to the boundary or something like that. So, I mean, so the toric boundaries of toric manifolds are extremely special, right? So I mean, they come from some rational polyhedral cone. So just assuming that the boundary is rational, I don't know. I mean, so how would you ensure this rationality of the cone or something like that? So I'm not sure about that.
If you could construct one whose boundary complex is not an NCA, that would be. But I don't think it's.
I mean, homologically, you can't do that. So in dimension 3, it seems unlikely you're going to not so many.
Okay, maybe some further discussion later. Okay, other questions? Okay, well, thank you very much. Very informative.
Thank you very much.